verification session. First, one quick announcement. Some folks have been asking how to get tickets for the farm event on Friday. Apparently there's a form on the farm website that you can use to still buy those tickets now. And I'm sure at the registration desk people can help you with any more issues there. So it's my pleasure to start the program verification session. This isn't like 20th century program verification where everyone expected that the grand challenge was to verify quicksort or something like that. I think each of the talks in this session takes a feature that's a traditional nasty thing to ask about in a question after a verification talk and shows how it can be handled nicely. And to start off, we're going to see how a mixture of programming effects can be fit into an elegant predicate transformer system. And Wouter will tell us more.
Thank you, Adam. So I wanted to actually start by giving a big shout out to my co-author, Tim. So Tim is one of my master's students, and he really deserves a lot of credit here. I started writing this paper, but I wouldn't have finished it without him. But unfortunately, Tim couldn't make it to ICFP this year, so I get to give the talk. So I can start by telling you about one of my all-time favorite papers, which is Constructive Mathematics and Computer Programming by Per Martin Löf. And it's this paper which set out this whole idea of a type theory also being a programming language. And it's just sparked all the research that we do into programming with dependent types these days. So there's a few versions of this paper online that you can find, and this one is actually given at a meeting for the Royal Society in London on computer science, mathematics, and logic. And Per wasn't actually supposed to be at that meeting, but he was flown in last minute to replace Dana Scott. And someone who was at that meeting was Edsger Dijkstra. And what Dijkstra would typically do when he kind of went to meetings or when he had an idea which was interesting but maybe not suitable for publication, or if he wanted to rant about something, he'd write this up. And then with his fountain pen, and then he would mimeograph it or something, duplicate it or Xerox it, and then send it out to all kinds of researchers doing related work. And he would kind of Xerox it again and send it on and on. So it's kind of like this analog blog or anablog or something. And anyhow, so in one of his trip notes, he talks about this visit to the Royal Society and that there was this interesting talk by the Swedish philosopher Per Martin Löf. But reading this, he's very positive for Dijkstra's standards. He was a very sympathetic speaker and convinced me at least that something, possibly of great conceptual elegance, was going on. So the point of this paper is to actually show that a lot of the ideas that Dijkstra was working on about weakest preconditions and predicate transformers and program calculation, they actually fit very nicely in this framework of Martin Löf type theory, especially if we use the modern languages that we have, like Agata or Idris or Kok. So I'll use Agata today. So this is the goal, giving a constructive account of Dijkstra's weakest precondition semantics in Martin Löf type theory. So let me explain some of the words in the title. So when I talk about a predicate, I'm talking about a value which goes from A to Z, of type A to Z. And if you're not used to programming with dependent types, which is fine, you might think of something going from A to bool, and that's a kind of good approximation, at least a first approximation. If you're not used to thinking about static types at all, this talk will be over pretty soon. So a predicate transformer is something which maps one predicate into another, like A to Z to B to Z. And the most famous predicate transformer is the one which you use to assign predicate transformer semantics, which is the weakest precondition. So if we have a function from A to B and we have the desired post, we compute the weakest precondition necessary to ensure that the function returns a result satisfying the desired post. And I left out the implementation here, it's 3 dots, dot, 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 but that's actually 2 dots too many because it's just function composition. So just to convince you of this, suppose you're given a function f from A to B and you have the post condition that it should satisfy, and you have an argument to the function, what's the weakest possible precondition that you need in order to ensure that f of x satisfies p? Well, that's p of f of x, right? So this is what I'll be talking about today. Throughout the paper, though, we use a slightly more general version. So sometimes you don't want to have a post condition which is just a predicate on B's, but you want to have a relation between the input, the output, and have that as your post condition. And this follows quite naturally as soon as you start using dependent types for your function here, where you have a dependent function and then you get a relation between the input and output, and then you compute the precondition. I have it on the slide here, but I won't use this definition much. So this describes predicate transformers. Let me talk a little bit about effects. So we're not only interested in pure functional programs, we're typically also interested in working with effectful programs that do things like diverge, use nondeterminism, mutable state, or throw an exception. And what I'll do is I'll kind of follow the recent work on algebraic effects and make a very careful separation between syntax and semantics. So I'll give the syntax by means of a free monad and the semantics using a predicate transformer. So what does this look like? So let me show some Agata code at this point. So I can give a free monad in the kind of the container style, where I define a data type, which is has 3 parameters, which is a C of type set, and this describes the kinds of operations I'm allowed to use. These can be like operations like get or put or branch if you have nondeterminism, or abort. And on top of that, I have the responses telling me for every command what's the return type that I get by issuing this command. And then I can use that in my clicker's stopped pointing. In the kind of continuation I have as a second argument of the step constructor. Or I can just return a result of type A. So I have pure and step, and these are the 2 things that I can do to build these kind of syntactic structures. And different choices of C and R give rise to different effects. So there's lots of examples. If you've read any literature on algebraic effects, these will be familiar. So you either can have a command abort, which doesn't give you any kind of information to return. In fact, it gives you 0, like bottom, so there's no continuation that you can write. You have things like state, where you have 2 commands, get and put, where the response for get is an S and the response for put is top or unit. You have nondeterminism, where you have a choice and a fail, and the response for a choice is a bool because you branch, and the response for fail is bottom again. Or you can even model general recursion. Here we're kind of taking a page from Conor McBride's work on Turing completeness totally free, where we give, if we want to kind of have a call to a generally recursive function of type I to O, our commands are just a single operation, which we call call, where we provide the input, and then the response kind of describes how to continue after receiving a result. But I won't say much about general recursion today. So now we want to compute semantics for these effects. So the obvious thing to do is, okay, let's look at a Kleisli morphism that kind of returns one of these free structures, and then apply our weakest precondition function that we saw previously. And then what you see is you have a function. This gives rise to a function of this type. But the postcondition here is a postcondition which kind of maps this free monad on B's to set. And I was giving this whole song and dance about how important it is to kind of distinguish syntax and semantics. Where here, if I write a postcondition of this type, I can observe things about the syntax. I can see how many get constructors there are. There's all kinds of things in there which maybe I want to hide, depending on what I mean by the kind of the syntax that I have in mind. So what I'd much rather have is I'd rather have a formula of this type, where I write a postcondition of type B to set, rather than free of B to set. So what's missing is the thing at the bottom of the slide, the thing which says, given the postcondition on B's, give a semantics to these effects to create a postcondition on free of B's to set. So what do these look like? Well, here's one example, which is almost the simplest thing you can do, which is how do you assign semantics to partial computations that can call abort? So what I've done here is the top line is the type signature, and then you see the weakest precondition call. But there's interesting stuff happening in the where clause. And there I describe how to lift one of these predicates on B's to a predicate over partial B to set. So if I'm returning a result and I want P to hold for all results, then, well, P of Y better hold. But if I'm calling the abort operation, then I want to kind of say bottom. And now the weakest precondition in this case is going to ensure that abort never gets called. So the weakest precondition guarantees that when the precondition is satisfied, the abort will never get called. There's other choices here as well, right? Whenever you define a syntax, you have a choice for semantics. I could choose, instead of bottom, I could choose top. And then I would have the weakest precondition that guarantees that if you return a result, it will satisfy P, but it doesn't tell me if the result will be returned or not. Or I can do things where I can require that P holds for some default value that I'd like to return. And there are other choices again. Nondeterminism is equally simple, right? When we have a pure, we require P to hold for X. When we have a fail, we say top. And when we have a choice, we make 2 recursive calls and take the conjunction. So what this is doing, it's requiring P to hold for every possible result returned by the non-deterministic computation. You have other choices again. If I replace top by bottom and conjunction with disjunction, I get kind of a gambler's nondeterminism, where I'm happy if P holds for one possible result, and I don't require it to hold for all the possible results returned by this list. And if you read the paper, you can find more about state and general recursion and these other effects that I mentioned. But I want to get on because it seems kind of like I'm doing a lot of work, and why would I do this, right? I mean, it's kind of cute that you can assign these weakest precondition semantics, but why bother with this in the first place? And the nice thing is that we can also assign these predicate transformer semantics to specifications. And then we can use a refinement relation to show that a program satisfies its specification or even derive a program from its spec. So that's what I want to get to in the rest of this talk. So what is a specification? This is something we can take straight out of any book on Hoare logic. We basically have a record which contains a precondition and a postcondition. So if we have a dependent function which goes from x in A to B of x, the precondition is the predicate on A, and the postcondition is a relation between the input and output types. I'll write these specifications with square brackets pre-post. And if we want to assign predicate transformer semantics to these specifications, what do we get? This is something that you can take kind of literally transcribe from any kind of literature on the topic. You get this thing, which basically guarantees that, well, the weakest precondition associated, given the desired postcondition P, what's the weakest precondition that should hold in order to ensure that running a program satisfying this specification will also satisfy P? It's that the precondition of our specification holds, and that for any result returned by the program that satisfies this specification will also imply P. So what this gives us is it gives us a predicate transformer semantics for specifications, which we can then relate to the predicate transformer semantics for effects that we saw previously. And this relation is typically called a refinement relation. So if you go to Wikipedia, which is the source of all knowledge, and you look up the page on formal specification, you can see that refinement is another approach to use probably correct refinement steps to transform a specification into a design. It should be provably correct, of course. But it kind of matches the way I usually do program verification, right? It's probably correct. So let me define refinement. So refinement is just the implication of the associated predicate transformers. So that is to say that if you have two predicate transformers which map predicates on B to predicates on A, I can construct a relation between them by saying that for all possible posts, I want that PT1 of P implies PT2 of P. And this relation, it's nicely, has all the properties that you want. It's reflexive, it's transitive, it's kind of morally asymmetric. And now to show that a program satisfies its specification amounts to showing a refinement between the predicate transformer semantics associated with the specification and the predicate transformer semantics associated with an effectful program. Of course, you can do other things with refinement. So you can also compare programs. Because we can assign semantics to programs, we can compare those semantics with refinement as well. And you get reassuringly familiar notions. So you can see, for example, that for partial functions, f is refined by g if g adds more points to f. For non-deterministic functions, using the kind of the all semantics, it corresponds to the subset relation. And if you have the gambler's non-determinism, the subset relation is reversed, which you would kind of expect, because if you know that P holds for one element of a kind of 7-element list, it's better to know that P holds for one element of a 3-element list. And then if you look at state, you get the usual weaker pre's and stronger posts. So what's one very important property of refinement is that it's compositional. So as pure functional programmers, we're kind of spoiled. We're used to having this notion of referential transparency, which will let us substitute equals for equals. And we can use this all the time as soon as we do any equational reasoning. But what's a nice consequence of all the machinery that we've constructed is that we get a very clean compositionality result, which says that for any 4 Kleisli arrows, if we try to do a refinement problem where we take the Kleisli composition of F1 and G1 and want to refine it to some F2 and composed with G2, we can break this up into 2 completely separate parts. And this isn't always true for when you start reasoning about effects, of course. So what we've seen so far is we've seen a bit of program verification, right? Where we take a specification, compute its predicate transformers, and show that it can be implemented by a program. And I've drawn the program here as a little syntax tree with a bunch of commands and values returned in the leaves. So what about trying to, instead of doing this kind of monolithic verification, do program calculation? Where I start with the specification, I can refine the specification until I have a finished program. And that's the original idea behind the refinement calculus. I think this fits quite cleanly in this framework by considering not just free monads that return an A, but free monads that return either an A or an unfinished kind of derivation problem. Please find an A that satisfies this specification. And we can assign semantics to these free monads just by kind of composing all the predicate transformers that I put on the slide so far. So then you get that you start with a programming problem which says, please find a program which satisfies this pre and post, and you can play out a command and says, okay, I'll try to issue this command, and I have two new specifications that I need to satisfy. I can do this over and over again, and maybe at S3 I think, oh, okay, this says I can actually find a value of type A which satisfies this specification. Let me return that, and then you can kind of go on and on and on until you've completely written your program. So, of course, it requires a little work, right? Because typically for every effect, you want to describe what it means or what work you need to do in order to, or how the specification evolves as you play out that command in the tree. And no one calculates programs, and this relies on this compositionality result. But I think this kind of technology is even useful if you do very big program verification, and you have this kind of specification, you have written your program, and you throw it at the theorem prover, and the theorem prover says, nope, I can't find the proof. At least what this gives you is like a small step debugger where you say, okay, let me feed a little bit of the program that I have in mind into the proof assistant. And then I can see two new programming problems, two new specifications that I need to satisfy. I think, oh, okay, that still looks okay. And I hit a loop, I think, oh, no, I need a stronger looping rate. And I can kind of freeze the verification state at any particular point in time. Okay, so I need to wrap up. I hope I've convinced you that something possibly of great elegance is going on here. And if you know the semantics of an effect and you have a pre and post spec, taking their predicate transformers combined, the spec can be refined to ensure that our programs ain't wrecked. Thank you.
So let me start with a question from Slido. This is an interesting one. I'm trying to reverse engineer what one does with an answer to this question. Can you generalize your predicates from returning set to returning something else, such as numbers? And this question comes from Ken Chan.
Yes. Let me think. So when I say set, I mean a type, right? Because I typically am, and this type can be any, so bool is obviously, you can take any Boolean and turn it into a truth values like 0 and 1, right? Saying that false is the empty type and 1 is the unit type. And if you're interested in numbers because you want to count something, you could turn that into a finite type with n elements. That would work, but set is more general. But I'd be interested to see what kind of application you have in mind for this.
Let's see. How about in the back?
Thank you. That was a great talk.
Thank you.
One of the interesting things that happens when you start to program with these algebraic effects is that you sometimes want to combine multiple such effects.
Yep.
And I'm wondering if you've looked at how you take the weakest precondition transformer for, say, state and one for nondeterminism and use them both at the same time.
Yeah, that's a really good question. So the good thing is that the syntax composes easily and the challenge is always the semantics. So I have a part of an answer, but it's not in this paper, unfortunately. But for Tim's master thesis, what he did once he kind of did all of this, he said, oh, I'll just write parsers now. So he kind of took parsers as being the list of successes, the usual composition of state and non-determinism, and he kind of showed how to write parsers and general recursion, right? So he didn't have to worry about the string getting any smaller and all of this. So it turned out to work quite well. It's not quite as clean as I would like yet, but we'll get there.
Okay, let's take another Slido question. Can you handle delimited continuation effects or some restriction of them?
Probably not. So we're just using free monads here, which is, and I'm not using kind of algebraic effects in their full generality, and maybe if I thought about it really hard, I could extend this to that, but I wanted to keep something kind of simple and first order, relatively first order for the free monads in the first approximation. But it's a good question for further work.
Okay, more audience questions. I saw some before, but I guess we have some effects in play and they went away.
The question aborted. Yeah.
Anything popping up here? I do have one more on Slido. Last chance to jump in front of it. No? Okay. This is an interesting one. What was the initial topic of the master's thesis?
So that's a very good question. The initial topic of the master's thesis, so Tim, he did a bachelor in maths and computer science, and he came to me and said, do you have anything on kind of maths and computer science? And he said, yeah, I have a half-finished paper and I can't kind of bring myself to finish it, and can you read it and help me? And he's like, yeah, this is super exciting, and then he just stormed off with it. So yeah, I just planted the seed, really. So.
Any other in-person questions? I think I can add one then. Okay. What are the most interesting refinements and/or program verifications you've done using this framework so far?
Yeah, so we've done a bunch of examples, and the focus kind of in the paper isn't on doing kind of very big proofs. We've done a lot of like the usual very simple things, tree relabelings, guaranteeing that a simple program doesn't call abort, you know, the usual kind of crawl before you run exercises. The next kind of interesting thing would maybe to do is to port this to languages which have better tactic support. If you want to get something realistic, do any kind of big program calculation or verification in this style. Yep.
Okay, great. So how about we thank Wouter and switch here? Yep.